Welcome back from the break. Now we will start looking into optimal control and later into deterministic dynamic programming. Then we'll take a second break and continue with the hand-in assignment and some more details and also some fun animations of how optimal control problems are solved numerically with the help of the toolbox that you get from this course. When we talk about optimal control, we can have as role model that we want to drive from point A to point B with a given time, and we want to do that with the minimum fuel consumption. The main difference between traditional optimization is that in optimal control we have a continuous variable that then becomes an infinite dimensional decision variable. In the same way as for the normal optimization problems, we have a cost function. The thing that differs is that the cost function usually depends on an integral of some state. A scalar can also be added, but for this particular problem it's more natural to work with the total fuel consumed, which is the integral of the mass flow. Mass flow is denoted with a dot over the m. Then we have constraints, and the main difference compared to traditional optimization is that the constraints are not regular equations. Instead, they are differential equations. So we're saying that we need to fulfill, for example, the vehicle motion equation here, and then the distance is the integral of the velocity. Finally, we have a function here, which is the fuel flow into the engine, and that one depends on our control variable, that is the gas pedal. Then we have constraint where we are starting, and we constrain where we are finishing. And finally we have other path constraints that says, for example, we need to fulfill the speed limits that are functions of where we are. And finally the gas pedal can be fully up or fully down, so we have also limited control actions. This is a very difficult problem to solve analytically in the general case. Only some special cases are solvable, and we will look at some few examples later in the online control lecture. In optimal control, the general problem formulation is as follows, where we have, similar like the fuel optimal control problem, we have an integral that can be something more general, but in our case it's very often total fuel consumed, or if you're looking at an electric vehicle, it's the total amount of energy consumed from the battery. Then we can also have a state of charge that's above a certain level. That can be formulated either as a hard constraint, or we can formulate it as a soft constraint like this, so that we're saying that it should be larger than 50% when we end. If it's less than 50, then we add an extra cost to say that we need to utilize fuel later when we are driving in the future. The first constraint is a system model. X here can be a vector valued function. It could be, like it was previously, 2 states, but could be any number of states needed to describe the system. Then we have the control, and then we have the time. Then we have the starting point that's defined. Where do we start? Finally, the controls need to be in their allowed set, and the states must also stay in a certain set, like we had previously control 0 to 1 in the gas pedal, and here the velocity needed to stay within the legal limits. Optimal control is a very old subject. There's a rich theory. We have old theory from calculus of variations. Much theory and many methods were developed during the 50s and the 70s, and they were successful in the aerospace industry, working with satellites and optimizing control of satellite trajectories. The theory and methods are still being actively developed, but if we look at some historically interesting points, it's the dynamic programming by Richard Bellman that was developed during the 50s. Then now we have a modern successor, that's model predictive control, that is relying upon optimization as a tool for optimal control. Now there's a high interest for collocation methods. There were a few during the 1990s, and then much interest has come after the year 2000, and this one is continuously expanding because we get better and better computers, so the computational platforms are helping us to evolve. As an advertisement, there's a separate course TSFS03 optimal control that goes through the theory of optimal control and lets you work with several methods that can be used to solve optimal control problems. Now we will jump into the main tool for the hand-in assignment number 2. We will work with the deterministic dynamic programming. In the general setting, we have the optimal control problem stated like this. We have the criterion or our cost function. We have the states. We have the constraints. We have an initial point and we have the constraints on controls and constraints on the states. Our state and our control are functions on the time interval. Now we search an approximation to the solution by discretizing both the state space and maybe the control signal. In this case, we have our time horizon. We start at 0 and then we go up to the end point. And the blue dot here represents that this is where we want to start. And the green dot here is where we would like to end. We are discretizing it in time and we're also discretizing the state space in the amplitude. And then we're looking at what states can be reached and what does it cost to reach the state. The problem, as you can see from the graph here, illustrates that this becomes a network problem. So the setting is to find the optimal control actions that minimize this cost function. And we have the states where we have a state transition function that tells how do we go from time k to time k plus 1 when we are applying our control u at step k. Then we have our initial condition and finally we have the constraints on the states and the constraints on the controls. It is also possible to add a disturbance here. This disturbance can be a stochastic variable representing some unknown, for example, unknown information about traffic or other things. And the difference between the one without the W and this one with here is that the one without is deterministic dynamic programming, while if we have added this uncertainty, it's called stochastic dynamic programming. The basic algorithm for solving dynamic programming is relying upon a function that we call the cost to go, and it's related to the cost function. The basic principle is that we start with the cost that we have at the final stage. In this case, if we want to reach this green point here, we have the lowest cost for this point. Then these can be higher costs and these can also be higher costs. You can, for example, rule out all of these if you are not allowing the state to end up here by saying that these are infinite. For example, in MATLAB you can use the inf value. For the hybrid vehicle, allow all of these to be viable, maybe with a certain deviation if we don't want to go there. Anyway, the basic idea is to start by knowing where we want to go, and then when we have determined the cost of being at any of these points, we start to evaluate. So we start to evaluate the cost to reach the final point from this node, then this node, then this node. And then when we know the best way to get to the final state, we store both the value and we store the path. For example, the best is to go there. Then we take the next point, we do the same thing. This will be illustrated with some procedures later, but the basic principle is that we build up this cost to go and then we propagate it so that we have the cost to go from all of these points. When we know the cost to go for these, we know that whatever we're doing here, it will not influence what comes later, so that we can decouple it and we can focus on propagating from step to step backwards in time, because we are focused on where we wanted to be. So let's jump to the algorithm, where we'll start by tagging these with numbers and then we will propagate. So the algorithm looks as follows. We set k equal n and we assign the final cost that we have, which is g of n. So the final cost is specified by this and it's placed there. Then we go one step down, so we go to n minus 1 the first time, and for all points in the state space grid we find the optimal point. So we search over all of these that have index k by taking the k plus 1. Initially this was jn, and then we are searching for each point what is the optimal path to reach the next point. If we have reached 0, then we have the solution. Otherwise we go to step 2, so we decrease it. So now we are at n minus 2 the second time, and we have already stored these costs. And we're calculating them by looking at the next part in the grid, and we're adding all possible path transitions to go from the current point to the next point, and we're evaluating which combination here gives the best combination for the previous point. Then, if we have reached 0, we return the solution. If we haven't, we go to step 2, where we decrease the iterator, and then we go through the procedure of filling the grid again. So, to illustrate this procedure, we will use a graphical representation. The graphical representation is based upon the fundamental idea to construct the cost to go. We have set the cost of Jn to Gn xn here, so this is the Gn costs that we're seeing. The next step now is to start to populate these with values so that we can get information about what's the cost of going from any of these points to the final point, and also storing the information which one is the best. So we start evaluating the first. The cost to go along this path is 0, the cost along this path is 2, the cost along this path is 4. So 4 plus 1 is 4, 2 plus 1 is 3, 2 plus 0 is 2. So this is the best solution for going from this to the end. In this one, we do the same thing again. We look at the cost that we have and we do this evaluation. So here we have to evaluate a bundle of arcs that tells us what is the cost to go from this point to all these considered points. We do the same thing. We find which one is the best. We store the arc and we store the value. Then we jump to the next one where we do once again the same thing. We search for the best way to utilize the previously stored costs to go and the arc costs to find the best way to come to the end. And then we continue down, down. And when we are finished with this one, then we jump to the next one and continue performing the evaluations. So this is the key idea behind the cost to go function and behind the deterministic dynamic programming algorithm. Now let's look at the arc cost calculations that we're doing. There are two ways of performing them. One fundamental thing is we know where we are and we also know to which places is it possible to go. So you know where you are and you also know all the places you can go to. There are two ways of calculating the arc costs. We can look at the state we're in and then we can look at how much does it cost to reach the next point that is at the end of the arc. So we're doing this for each individual arc. And this can be seen as the quasi-static approach. We know the movement that we're going to do and then we calculate backwards until we, for example, get the fuel consumption for making that step. Another way of approaching it is to make a grid over the control signals and evaluate the control signals and then interpolate the arc costs over each arc. This is discussed very much in the book, so I will not spend much more time on it in the lecture series. The first approach is straightforward if you are comfortable with the quasi-static approach, and we will use this during the hand-in assignment. Since you will implement and do computations of the solutions in MATLAB, you know that it's very important to utilize matrix calculations so that you don't do for loops over the arcs. So you calculate the whole bundle of arcs in one step. So you just write up an equation and you use MATLAB's powerful matrix computational tools. Then when you have done the calculations, you add boundary and constraints checks. For example, you check if the current to the battery fulfills the limitations on the battery. There are some pros and cons with dynamic programming. We know that we get a globally optimal solution for all initial conditions. So it's guaranteed to really get the global optimal, which is kind of nice. But we only get the solution within the discretization. So if we change the discretization, we can get other solutions. In the next sequence, we will look at an example where this happens. Another nice thing why it's been adopted so much is that it can handle nonlinearities and constraints in a very general format, so you can implement more or less any type of system or vehicle. The third advantage is that it has a time complexity that grows linearly with horizon, and you can use the output and the solution as a reference for comparison. So if you solve an optimal control problem, you can use that as a benchmark for your real-time control problem at a later stage. The disadvantages are that it's non-causal, so we have to have full information of the future. And another is that the time complexity of solving the problem grows exponentially with the number of states. We have what we call the curse of dimensionality, and 2 to 3 states are often at the limit of what we can do with today's computers. Having mentioned the time complexity, one might get discouraged by the exponential growth, but to illustrate that this is quite a huge step forward compared to enumerating all solutions, we look at the following example. We have a problem where we are running over 200 seconds with a discretization of 1 second. So we have 200 steps to fulfill. So that's the time horizon. Then we have a control signal that's discretized with 10 points, and we have a state space that's discretized with 1000 points. If we assume that one evaluation of the model takes 1 microsecond, then for a brute force solution where we evaluate all possible combination of the control sequences, we get 10 to the power of 200, which gives us 3 times 10 to the power 186 years. Considering that the universe is only 13.8 times 10 to the power of 9, we see that this is not an option to finding such a solution. But if we solve it with dynamic programming instead, the number of evaluations will be 2 million, which gives us a solution time that's 2 seconds, which is quite nice for a desktop computer. We can sit and iterate and try new solutions and get a new solution every other second. With that, we have covered optimal control and we have covered deterministic dynamic programming. Now I think it's a good time to take a second break and digest the optimal control and the procedure for solving dynamic programming using this propagation method.